Welcome to Brain Vision.
Hey guys, let's do problem 101. In this problem we need to calculate the molar flow rate. First we need to look up what is the critical temperature and critical pressure of the components. The critical temperature and critical pressure are in the Kelvin and atmospheric pressure unit. The components are methane, which is having the critical temperature of 190.7 Kelvin and critical pressure is 45.8 atmospheric pressure. Another one is ethane. Ethane is having the critical temperature of 305.4 Kelvin and the critical pressure is 48.2 Kelvin. And another component is ethylene, which is having the critical temperature of 283.1 Kelvin and the pressure is 58.5 atmospheric pressure. Given the temperature and the pressure of the system are 90 degrees Celsius, let's convert it to Kelvin scale. Therefore it is 363 Kelvin and pressure of the system is given as 175 bar. Let's convert it to atmospheric pressure by dividing it by 1.01325. Therefore the pressure is 172.7 atmospheric pressure. Next we need to calculate what are the pseudo-critical temperature and pressure. The pseudo-critical temperature is, we can calculate it using the case rule. The mole fraction of a component multiplied by the critical temperature of the component plus mole fraction of another component multiplied by the critical temperature of that component, and so on. In this case the mole fraction of methane is 0.15. Mole fraction of ethylene is 0.6 and mole fraction of ethane is 0.25. Therefore the pseudo-critical temperature of these components are 274.8 Kelvin. And similarly we need to calculate what is the pseudo-critical pressure. Again we can use the case rule. Critical pressure of ethane is 45.8 atmospheric pressure. Of ethylene it is 58.5 atmospheric pressure, and for ethane it is 48.2 atmospheric pressure. Therefore the pseudo-critical pressure is 49.2 atmospheric pressure. Next we need to calculate the pseudo-reduced temperature and pressure. The pseudo-reduced temperature is the temperature of the system divided by the pseudo-critical temperature. The temperature of the system is 363 Kelvin. Pseudo-critical temperature is 274.8 Kelvin. Therefore the pseudo-reduced temperature is 1.32. Similarly the pseudo-reduced pressure is pressure divided by the pseudo-critical pressure of the system. So 172.7 atm divided by 49.2 atm, which gives us 3.51. Now for this pseudo-critical temperature and pseudo-critical and pseudo-reduced temperature and pseudo-reduced pressure, the Z factor is 0.67. Now we can calculate what is the volume flow rate, and then we can use the compressibility factor equation to calculate what is the molar flow rate. Let's do that. We know volumetric flow rate is equal to velocity of the system multiplied by the cross-sectional area of the pipe. The velocity is given as 10 meter per second, and area can be defined as pi r square or pi d by 2 square. Given the diameter of the pipe is 2 centimeter, let's convert it to meter. Then 2 centimeter divided by 100 centimeter divided by 4. Then we get the volumetric flow rate of the system is 0.00314 meter square per second. Now we can use the compressibility factor equation of state. And we can calculate what is the flow rate. The pressure of the system is 172.7 atmospheric pressure. The volumetric flow rate is 0.00314 meter square per second. Let's convert it to minute. We need to multiply it by 60 seconds per minute divided by compressibility factor 0.67 multiplied by the gas constant, which is 0.0821 meter cube atm kilomole inverse 1 Kelvin inverse 1, and the temperature of the system 363 Kelvin. As we do this calculation, we will get 1.63 kilomole per minute as the flow rate. The pipe can hold the mixture at flow rate up to. Therefore, the pipe can hold the mixture at flow rate up to